Hey everyone, in Physics 4DS land, it is Dr. Carroll here. We are looking at Unit 2, Lecture 3. We're going to look at gravity today. In your mini text, it's page 158, but I'm going to be elaborating on that. Force of gravity, Fg, there's a direction. It's towards the center of the Earth or towards the center of any object. We're talking about a really large object having a effect on a much smaller object, then that smaller object will be attracted towards the center of the larger one. Force of gravity is also known as weight, which is m times g. Little g is also called the gravitational field, and we're going to talk about that as well in this lecture. So let's start it here. It's always an attractive force, always directed towards the center of the Earth, and the force of gravity is an inverse square law, and there's a few phenomena in physics which are using inverse square laws, including light intensities and sound intensities, and Coulomb's law, which is electrical force, which we get into way later in this course, but we do. R is the distance from the center of the Earth, or whatever our larger object is, to the smaller object, or between 2 points. Some people use lowercase d, but r is more common, I've noticed lately, so that's the one that I'll use most of the time. The definition of the force of gravity is capital G m1 m2 over r squared. So the farther away you get, let's see, double the distance between the 2 points, the force of gravity is just a quarter, not a half, but just a quarter of what it was before. That's what we mean by inverse square law. The masses are directly proportional with relation to the force of gravity. So the greater the mass of one, two, or both, the greater the force of gravity. Sometimes the larger mass is written as a capital M and the lower mass is a lowercase m, but it doesn't have to be that way. The constant proportionality, capital G, is called the universal gravitational constant, and it is, put 11 there, that's an 11. 6.67 by 10 to the minus 11 newtons meters squared per kilogram squared. Yeah, you don't have to memorize that constant. That is the value which says that if there's two regular people, the gravitational force of attraction between them is going to be pretty darn small because G is so small, 6.67 by 10 to the minus 11. But when we're talking about huge things like the mass of the Earth, well then you cannot ignore the effect of gravity. So you'd be given this data too. Here's the mass of the Earth. Here I'm assuming it's a perfect sphere. We know though that it's actually squashed on the poles, so the poles have a greater gravitational field than the equatorial regions of our planet. But let's just start by assuming a sphere. So the mass of the Earth is 5.98 by 10 to the 24 kilograms from astronomical measurements, and the radius of the Earth is 6.38 by 10 to the 6 meters. Sometimes you'll get questions where instead of meters you're going to be given kilometers. Be careful on that. Make sure when you're doing gravitational force calculations that the distances are in meters and the masses are in kilograms. So let's suppose that we have a 1 kilogram basketball or medicine ball on the surface of the Earth, and so, the force of gravity would be 6.67 by 10 to the minus 11 times the mass of the Earth, which is 5.98 by 10 to the 24 kilograms, times 1 kilogram over the distance from the center of the Earth to the surface, 6.38 by 10 to the 6. I'm going to square that, and the gravitational force will be 9.8 newtons. So we say that a 1 kilogram object at Earth's surface will feel 9.8 newtons of force. Another way to say that is the gravitational field at the surface of the Earth is 9.8 newtons for every kilogram. And so you get G mass of the Earth over r squared. So in other words, G equals force of gravity over the smaller mass, m2. So you get G m of Earth over r squared. And the gravitational field can be different depending on the distance from the center of the Earth that you are, where you're evaluating the gravitational field. For example, if you're evaluating it at a point higher than the surface of the Earth, then the gravitational field is going to be smaller. Like here, if I draw just an arc here, here's the center of the Earth, there's the radius of the Earth, but maybe I want to get the gravitational field at a point way up here. So that is my altitude, or my height, h, or altitude. Then my r would be the height plus the radius of the Earth. And so that gets larger, then the gravitational field gets smaller until it's essentially zero, and then you are weightless, right? Weightless in Seattle. So here's an example, and you can look at your mini text to get the picture of it. But we have a two objects, a really large object, 300 kilograms, and a small one, 40 kilograms. And we want to get the force of gravity between them. It's always an attractive force. So you just plug in your g, m1, m2 over r squared. So 6.67 by 10 to minus 11 times 300 kilograms times 40 kilograms over the distance between them, 1.5 meters squared. And the gravitational force is 3.6 by 10 to minus 7 newtons. So you could say that's the force of attraction of object or on object 2 due to object 1, and it's the same as the attractive force of object on object 1 by object 2. So they are mutually attractive force. Example 2, and I'm just going to flip open to the page here, page 162 in the mini text, and we're going to get the value. Oh, you can hear the pages opening, can't you? Actually, it's on to page 163. Calculate the force of attraction between a 1 kilogram melon and Earth. Okay, so I could, knowing that the surface of the Earth, the gravitational field is 9.8 newtons per kilogram, and it's 1 kilogram, so it's 1 kilogram melon at the surface times 9.8 newtons per kilogram. So the kilograms cancel, and you get a force of gravity of 9.8 newtons. I could do it the long way, where I could take force of gravity is g m1 m2 over r squared, plug those all in, and I'll get 9.8 newtons as well. Okay, example 3 asks you to find the weight of a 100 kilogram rugby player using both forms of the equations. Well, you can use the long form. If I know the rugby player is on the surface of the Earth, the weight is the force of gravity felt by the rugby player due to the center of the Earth. The Earth is pretty darn big. 100 times 9.8, so 980 newtons. So if you want to lose weight, you might go to the moon. The moon's gravitational field constant is much smaller. No, you don't say gravitational field constant, do you? You just say gravitational field strength. Gravitational field strength at the moon is just 1.62 newtons per kilogram, so it'll be 162 newtons. So if you want to lose weight, just Mr. or Mrs. Rugby player, go from the playing a game at the surface of the Earth to playing a game on the surface of the moon. Okay, there you go. The next example, we have a 60 kilogram earthling. This one's not in your... this is looking at the tables at the bottom of page 164. So we got the force of gravity is 60 kilograms times 9.8 is 588 newtons. Then at the moon it will be 97 newtons. And just looking at charts, and you can find these at all sorts of places on the internet, you see that Mercury, Mars, Venus all have gravitational field strengths less than Earth. Okay, so remember, you're looking at both the mass of the object and its radius, its average radius, and all of those are going to be less than the Earth. And then you're going to have some other ones, some of those bigger planets farther from Mars, which will have gravitational constants greater than 9.8. Next example talks about a 1,000 kilogram satellite. What is its weight? 32,000 kilometers from the Earth's surface. So the altitude, ALT, is 32,000 kilograms. The satellite is 1,000 kilograms, so that'll be M2. That's got to be smaller than the mass of the Earth. So the Earth's mass will be M1. And what students sometimes forget is to take the 32,000 and convert it to meters. So that's 3.2 by 10 to the 5. 1, 2, 3, 4. 3.2 by 10 to the 4 kilometers. Each kilometer is 1,000 meters. So 3.2 by 10 to the 7 meters. Add that to the radius of the Earth, 6.38 by 10 to the 6 meters. And you get a radius of 3.838 by 10 to the 7 meters. Okay, so you have to add the distance from the center of the Earth to the surface, add that to the altitude, and you get your distance from the center of the Earth to the satellite. That is your R. So now we plug it in. You get force of gravity is G M1 M2 over R squared. So 6.67 by 10 to the minus 11 times 5.98 by 10 to the 24 times 1,000 divided by 838 by 10 to the 7 squared. The mini text may do it a different way, but when all is said and done, you should get 271 between that and 272 newtons. Okay, I'm not going to bother with this assignment this year, so don't worry about that. Okay, those are examples related to gravity, and again, to summarize, force of gravity is G big M little m over R squared, or it's also little m times G, where G is Gm over R squared, the gravitational field strength. Okay, so I might as well push on because we want to look at the last topic in the short chapter. You will get some practice problems on gravity very soon. And let's look at one more force here, which is called the normal force. Normal force, you may have talked about it last year. I don't know why this says physics and physics. I don't know what that's all about. Physics ... Yes, I agree with that. So let's look at what's called the normal force. When you think of normal in physics, think of perpendicular. So let's say we have someone just standing on a level ground here. So that person is going to feel a force of gravity because there's the center of the Earth here. So we just talked about the force of gravity, which is mg. And if that person isn't sinking into the ground or flying like Harry Potter into the sky, then there's going to be a normal force because the person is in contact with the surface and the person is in static equilibrium. So my net force is gravity going down plus the normal force going up, which is going to be F and a capital N. Some books use lowercase n when I'm looking here, and our book will use lowercase n, but others use capital N, so just beware that both can be used. So if that's net force and it's static equilibrium, then the force of gravity and the normal force are going to be opposite to each other. Okay, I could have, here I have a magnet stuck into a fridge, and so the magnetic force is going into the board. Remember these little X's from last year mean going into the board, and dot mean going out of the board. So you have magnetic force sticking the magnet to the fridge, which is going into the board, and then you have a normal force going out of the board. Now there's other forces here, right? There's gravity going down and then friction keeping it from moving down. But those are other forces. We're going to get to friction in our next chapter. So the normal force is coming out of the board. Here we have someone on a ramp and gravity is going down, but the normal force is perpendicular to the gravitational force. So the normal force isn't the same as the gravitational force in this case. We're going to learn in our next chapter how we can break down gravity into perpendicular and parallel components, and how that's related to the normal force. Okay, here we have example 6 on page 169 in the mini text here. We have a person sitting on a box, and the person's mass is 40 kilograms. So the force of gravity is 40 times 9.8, or 392 newtons going downward, and then the normal force is coming up at 392 newtons. Okay, if the planks in the crate weren't strong enough, then you wouldn't be able to support the weight of 392 newtons. So in construction, you have to darn well know your normal forces, or else you're going to be in big trouble. Here in example 7, we have the person's on the crate, but there is a crane which is just starting to lift that person off the surface of the earth. Not the surface of the earth, the surface of the crate. Not quite, but just starting to, so your normal force is going to decrease. Now, your crane was 92 newtons. If we're still in static equilibrium, so the person isn't quite lifted off the surface, so you have the normal force and the crane force are both going in the same direction because the crane is lifting up. Gravitational force is going in the opposite direction. So I really shouldn't put these vector symbols here because I've made my vector addition and subtraction all already burying that in. So the normal force is the gravity minus the crane. So 392 minus 92, which is 300 newtons. And then you stop and you think for a second. Yeah, that makes sense. You've already relieved the stress, if you will, by 92 newtons because you've got that crane there. So the normal force has now been diminished from 392 by 92, so it's now just 300 newtons. So that's a way to look at normal force, and so that's how that works with the crane. Let's look at some questions here. And I'm just flipping here. 188, number 36. Then I'm going to just check the mini text so you see how that all works. A 20-gram fridge magnet is being held onto a fridge by a 0.9 Newton force. What's the normal force? Well, the normal force, if it's 0.9 newtons going in, the normal force is 0.9 newtons going out. The 20 grams is irrelevant to answering that question. 37, this is a question I like to ask on quizzes, tests, etc. You have a person, and that person is exerting, it's a man in this case, a force of 21 newtons up, holding a light fixture, okay? And the light fixture mass is 1.4 kilograms. So the mass is 1.4 kilograms, so the force of gravity is 13.72, is that right? If I go 9.8 times 1.4, 9.8 times 1.4, I get 13.72, that's right. So I got 13.72, that's gravity going down. I'm holding up with 21 newtons. The question is, what is the normal force? So again, you want to have a balance. You want to have static equilibrium. You don't want that light fixture crashing to the ground, and you also don't want to shove it up through the ceiling tile. So the net force is 0. So that's going to be the force applied, right? The force applied by the man going up and then the normal force and gravitational force are going the other way. So I bring the normal force to the other side, and it's going to be the force exerted by the man, 21 newtons minus 13.72. Excuse me. So the normal force is 7.28 newtons. Okay. Now just to show you what this mini text is, I'm going to have to minimize that for a second, and let's get to here. Page down. So this is selected pages, not much, but selected pages from an old textbook that I used to use. So you have the most important stuff here for practicing, and here we have the stuff we started earlier today with gravitational constant. Force of gravity is proportional to m1 m2 over r squared, and see everything directed towards the center of the Earth. There's the example 1 we looked at earlier today. Example 2 we looked at earlier. The rugby question. Example 3, some data. Oh, here's something interesting as we just look through things. Look how Winnipeg has a gravitational field constant of 9.81, whereas on Ecuador, Quito, capital of Ecuador, it's just 9.78. Now we're going to round off to 9.8, so we're not going to make a big deal about it. But technically, Ecuador places have a lower gravitational field because the Earth is really an oblate spheroid. Oh, okay, I don't have a drawing thing in this. I see. I used the what did I use here? Adobe Acrobat. Okay, whatever. You know what an oblate spheroid is. Like a squashed basketball. So it's greater at the poles, and Winnipeg's closer to the poles. Look at it. It's 59 latitude compared to Ecuador, which is 0. So the gravitational field strength is lower at the equator. This is why rocket launches usually happen closer to the equator, because then you aren't fighting as much of your gravitational force to get into orbit, and every little bit counts in the space world. Some questions there. Pictures from the normal force. Notice sometimes the normal force can be it's not always going up, sometimes it can go down. Here's a horseshoe magnet, and so the magnetic force is going up, so the normal force is going down, and that's okay. There's that crane example we looked at. Flow charts. This mini text likes to use flow charts a lot. You can use them if you want. I'm not a big fan of them. And then friction. Well, friction is going to be our next topic, and it'll be in Unit 3. So there you have it. Okay, and I'll give you some normal force questions to practice as well. Have fun.